Today, we're going to take a deeper look at the hardware components of a programmable logic controller, or PLC. Up to this point, we've talked about what PLCs are and why they are used in industry. But in order to fully understand how a PLC works, we need to break it down into its individual parts. Think of it like looking under the hood of a car. If you know the parts and how they connect, you can understand how the system functions as a whole. In the next two lectures, we'll focus specifically on the input and output sections of the PLC. These are the parts that allow the controller to interact with the outside world. The CPU is the brain, but the I/O is like the nervous system. It carries information in and sends commands out. We'll cover different types of I/O modules, including fixed versus modular PLCs, discrete inputs and outputs, backplane power, and how outputs drive loads through relays, transistors, and triacs. Along the way, I'll show you diagrams and schematics that explain how signals move from a push button on the shop floor through the PLC and out to control something like a motor starter. By the end of this lecture, you should be able to identify the major hardware sections of a PLC, explain the role of input and output modules, understand how discrete I/O works in on or off devices, recognize why power distribution relays are important. This knowledge forms the foundation for everything else we'll do with PLCs, because programming only makes sense when you understand the hardware you're controlling. Let's get started. The input-output section of a PLC connects the controller to the outside world. Fixed PLCs have built-in I/O terminals that limit the number of devices that can be connected, while modular PLCs use plug-in I/O modules that can be expanded or customized for the application. The I/O acts as the bridge between the CPU and field devices, allowing the processor to receive information from sensors and send commands to actuators. This diagram shows the arrangement of a modular PLC system. On the left, we see the power supply, which provides the necessary operating voltage to the PLC system. Next to it is the processor module, also called the CPU. The CPU is the brain of the PLC, responsible for executing the program, processing logic, and making decisions. To the right, we have a series of slots labeled 1 through 6. These are where the I/O modules are installed. The I/O modules form the interface between the controller and the outside world. Input modules bring information in, and output modules send control actions out. Together, they form the essential link between the program running inside the CPU and the physical process happening on the factory floor. One of the advantages of modular PLCs is the ability to place I/O modules closer to the field devices they control. This setup reduces the amount of wiring required, which can save both installation time and cost. To make this possible, PLCs use communication modules. These modules allow a remote I/O rack to be connected back to the local rack, where the processor is located. In the diagram, the box on the left represents the local rack. It contains the power supply, the processor, and some local input and output modules. These modules connect to nearby devices, like a motor controlled by a start/stop push button. On the right is a remote rack, which also contains input and output modules, but no processor. Instead, it communicates back to the processor in the local rack through the communication link shown in red. This remote rack is positioned closer to devices like sensors and actuators on a hopper system. We use the terms local rack when the I/O is in the same chassis as the processor, and remote rack when the I/O is physically located away from the processor. The key takeaway here is that remote I/O greatly improves efficiency in large facilities by minimizing long runs of wiring and keeping the processor centrally located while the I/O is distributed near the equipment. Some PLCs use what we call combination I/O modules. These modules include both inputs and outputs in one unit. Inputs connect devices such as switches and sensors, while outputs drive devices like lights or relays. Status LEDs provide quick feedback on which inputs are active and which outputs are energized. These modules save space and cost in smaller systems. Though in larger systems, separate input and output modules are often preferred for flexibility. The discrete I/O interface module connects field devices that operate in a simple on or off manner. These are sometimes referred to as bit-oriented devices because their signals are either a 1-4 on or a 0-4 off. On the input side, devices like push buttons, limit switches, and proximity sensors send simple on or off signals. On the output side, the module controls devices such as indicator lamps, relays, or motor starters, energizing or de-energizing them. Discrete I/O represents the most basic type of PLC interaction and is the foundation of most automation systems. All PLC modules receive their operating voltage and current through the rack backplane, which is powered by the system's power supply module. This power supports the electronics on the I/O modules, but does not power external field devices. Loads such as motors and solenoids require user-supplied external power, often from a dedicated DC or AC supply. The backplane ensures that each module inserted into the rack receives the necessary operating power. This graphic shows the block diagram for one input of a typical alternating current AC discrete input module. The input circuit is composed of two basic sections, the power section and the logic section. An optical isolator is used to provide electrical isolation between the field wiring and the PLC backplane internal circuitry. The input LED turns on or off, indicating the status of the input device. A bridge rectifier changes AC to DC, while a Zener diode ensures that only voltages above a certain threshold are accepted. The signal passes through an optical isolator, which separates the high-voltage field wiring from the low-voltage logic circuits, protecting the CPU. Finally, the module outputs a clean DC signal to the processor, with an LED indicator showing the input's on-off status. A discrete AC output module takes a digital signal from the PLC processor and uses it to control an external device like a lamp or motor starter. The signal first goes through logic circuits, which determine whether the output should be on or off. It then passes through an optical isolator, which protects the low-voltage PLC from the high-voltage AC load side. The isolated signal drives an electronic switch, often a triac, that connects 120 VAC power to the load. An LED status indicator lights up whenever the output is energized, providing quick feedback. In this way, the module safely translates the CPU's logic signals into real-world control of AC-powered devices. Individual AC outputs from PLC are usually limited by the size of the triac in the output module. Most triac-based outputs can only handle 1 amp to 2 amps of current. That is fine for small loads like indicator lamps or small solenoids, but it's not nearly enough for larger devices like motors. So how do we control larger loads? This is where an interposing relay comes in. The PLC output doesn't directly power the large motor. Instead, it energizes the coil of an interposing relay, which then closes the CR contact. This completes the circuit for the motor starter coil M. Once the motor starter coil is energized, it closes the three-phase power circuit to the motor, allowing it to run. This arrangement allows a small, low-power PLC output to indirectly control a much larger load by using the relay as a middleman. The PLC only has to energize the relay coil, while the relay handles switching the heavy current required by the motor. The main takeaway here is that interposing relays are essential whenever the output current demand of a load exceeds the capacity of the PLC's triac output. Discrete output modules switch field devices on or off using one of three technologies: relay, triac, or transistor. Relay outputs use mechanical contacts and can switch both AC and DC loads, but are slower and subject to wear. Triac outputs are solid-state devices designed for AC loads, offering durability but limited to AC only. Transistor outputs are solid-state devices for DC loads, providing fast, reliable switching. The choice depends on whether the application requires AC or DC control and the need for speed versus versatility. In the next lecture, we will examine analog input and output modules.